Hello, my name is Manuel Avidia. This is Project 36 for Senior Design, the Slingshot Spider. Our Senior Design group was tasked with creating a mechanism that would replicate or exceed the acceleration that a slingshot spider is able to meet with its web in a nature setting. Our objective was to design a catapult that would meet 1/10 of the acceleration of the slingshot spider. And with our ANSYS analysis, we showed that the web was actually necessary to achieve these accelerations. We then confirmed our results with our physical model and our experiments, and we actually exceeded our goals.
This is Tesfaye Legacy, and in this slide we will explore the inspiration and the background of the spider. Shown is a real spider that we are basing our design from. It is a three-dimensional cone configuration that reaches a really high acceleration. To be specific, it reaches 130 G, which is just about 1,300 meters per second squared. And to put this into even more perspective, that is about 10 times the amount of speed a fighter pilot can withstand before passing out. The spider also anchors the web as it pulls it back, and it is found that the total displacement of the web is a primary source of the elastic energy storage. This concept will be explored in further detail in the later slides.
Now let's talk about how we can reproduce this web mechanism in real life.
Hello, my name is Tom Bates, and I'll be discussing Design Option 1. The main feature of this design is the hexagonal sling mount at the front of the design that allows for the installation of a web-like slingshot system. The back end features a square plate to later bolt on a winch mechanism for the purpose of pulling back the web and maintaining tension until firing. The entirety of this frame is made of 3/4 inch aluminum square stock.
Hello, my name is Gunnar Waldvogel, and I will be talking about Design Option 2. Design Option 2 takes inspiration from a crossbow. It uses a trigger mechanism, and it uses a linear set of lines instead of a conical web design. This also features the ratchet similar to our other designs, and this one has a foot design to help it sit on the ground or on any unsturdy surface while we're shooting to help minimize movement while shooting, and this design would most likely be made out of wood and maybe metal.
Hi, I'm John Garrigan. Today I'll be discussing Design Idea 3. The main feature of this design is that it would have a hinged base that could vary the angle of launch. This would be done using some sort of motor. It also features a circular frame at the front of it that would hold radial lines and attach that to a mesh or cloth-like pouch. This pouch would hold the projectile, and this system would be brought into tension using a pulling mechanism such as a winch. To release the tension, a trigger mechanism will be used, and this would allow the projectile to be launched. This design idea was one of our original ideas, and it helped us brainstorm other ideas.
Here is Design Option 4. I was going for a slingshot somewhat similar design. It features kind of like a pocket to hold the projectile that would be launched, had a basic latching mechanism to it, and it was able to theoretically reach more pullback due to the roller design that was implemented at the front of the build.
Next, we created a decision matrix in order to rank our ideas. The ranking was broken up into 4 categories: safety, performance, reliability, and build difficulty. Performance held the most weight for us because high acceleration was what we were striving for. Next, reliability was not a major concern as we were only tasked in creating a proof of concept. The designs could all be manufactured if chosen. Therefore, build difficulty did not hold too much weight for us. From there, we ranked each design as a team, and then we decided that Design 1 would be the one moving forward.
Now that we established which design was chosen, let's go over the revisions.
Figure 1 shows the original design chosen by the decision matrix. In Figure 2, the final design, the first revision is a diagonal support bar instead of square to increase support to the web mount. We also changed the material from aluminum to steel for easier welding and increased the thickness to 1 inch due to it being more readily available from suppliers. The screws on the web mount were changed to eye bolts for easier attachment. And finally, we decided to buy the winch and quick release mechanism from a supplier instead of making it ourselves to save time in the building process.
Next, we will discuss the web mechanism.
3 different web designs were subject to a central load. Each design adds more axial strands, resulting in a web-like sling system, shown in Figure 3. Using the total deformation, we were able to find spring constant for each design. The difference in spring constant from Figure 1 to Figure 3 was nearly 235 newtons per meter. The higher the spring constant, the more tension we could add to the web, resulting in higher launch accelerations.
Hi, my name is Justin. Today I'm going to talk to you about the material selection for our web design. So we had 2 options originally. The first was the paracord, and the second was rubber tubing. Now the paracord has a 30% elongation requirement, and once we got our hands on that, it turned out not to be enough for our project to satisfy it. That's what led us to using the rubber tubing instead, which has varying elongations, and this allows for us to actually test the pellet velocity with different elongations in that web exact.
The video below captures a test launch of our web design. In order to capture it, we used a slow motion camera, and then we ran the video through a tracking software. From there, we created a ruler that we put in the background of our video, and it measured out increments of 0.3 meters. By using this ruler, we could stop at each frame and then calculate the distance the projectile travels in that exact frame. Then, given the time of each frame and the distance traveled in each frame, we could then calculate the velocity of the projectile.
Now I will talk about how we obtained and analyzed our data. We did 2 different web designs and did 2 separate trials for each design. We used a Galaxy Note 10 to record each launch and tracker software to analyze the video. This allowed us to obtain a velocity, which then allowed us to calculate the acceleration with the equation you see. If we compare our web design's acceleration to the Slingshot spider's acceleration, you can see that the acceleration that we got was much higher than the Slingshot spider's acceleration. Our original goal was 1/10 of the acceleration of the Slingshot spider. We exceeded that goal, and it just shows that this is not an effective way to compare. The Slingshot spider is very small, and if you scale it up to the size of our web design, we're not really sure if our design would be better or worse. To fix this problem, we decided to look into the energy density. The energy density is the elastic potential energy in the web divided by the mass of the web. To do that, we first had to find the spring constant. This was done by measuring the force and dividing by the displacement. Once that was found, we were able to calculate the potential energy in each trial, and then dividing by the web design's mass, we were able to get the energy density. The Slingshot spider's web has an energy density of 3.92 kilojoules per kilogram. Our highest energy density is web design 1, and it has an energy density of 0.72 kilojoules per kilogram. We are 1/5 away from the Slingshot spider energy density, and this just shows that we exceeded our goal of being within 1/10. And this is a much better way to compare it instead of acceleration, because it counts for the size difference between our web design and the Slingshot spider.
So in conclusion, we explored the background, designs, various redesigns, calculations, the video analysis, and the data analysis. And we proved that we exceeded our initial goal, which was to reach 1/10 the acceleration of the spider. Thank you.